When working with the law of sines, one of the cases that we run into is the side-side angle case, which we abbreviate SSA. And we also refer to this as the ambiguous case because there's not one unique triangle. There's not necessarily one unique triangle that is represented by a given set of information. So if we're given two sides and one of the angles that's not between the two sides, there's no guarantee just by looking at those values that we actually have a triangle. Okay, we have to look at it a little bit more to make sure that we actually do have a triangle that corresponds to that given information. And to the other side of, not only could we have a triangle, it's possible that there are two triangles that correspond to that given information that we have. Okay, and so the side-side angle case is a little bit more troublesome than the other cases that we deal with law sines and cosines. And so just to kind of explore why that happens with the ambiguous case, let's take a look at this graphing illustration here that was created by Jason Slobey. He's a user on geogebra.org. So on this graph here, we are given angle A is 51 degrees, and the side next to angle A is side B, and we're given that has a length of 12. And then the side opposite angle A, which is side A, has a length of 10. Okay, we do not know the measure of the angle at the top, which we could think of that sort of as angle C. We do not know the length of the bottom side, so we could think of that as side C, right? We do not know that length. And so the situation here is we kind of know enough values to possibly have a triangle, but maybe not. Because we actually don't know where side A is actually supposed to be, because we don't know what the angle is at the top, and we don't know where it's supposed to touch at the bottom. Okay, and so it's kind of this unclear value. Okay, so one thing that might be helpful to start with, if we're given this example or just any example in general, is try to figure out how high or what is the height of that triangle. Okay, and we'll look at this here in a second, but again, he has already included this in the graph here. So the height of the triangle, so to figure that out, we are going to draw a line from the angle between the two known sides. Okay, so we know side A and side B. So I'm going to draw a line from angle C at the top down to side C at the bottom, and I want that intersection here to be a perpendicular. Okay, and he's already had this value computed to be a length of 9.3. So the height of this triangle is 9.3. So what does that tell us? Okay, well, first, look at, if you draw that vertical height down, this is kind of how we can figure out what the length of that height actually is. Notice that it forms a right angle. It's perpendicular, forms a right angle at the bottom side. And that actually creates a right triangle with angle A and side B. So if we know angle A and side B, then we can figure out the height just using sine. The sine of A has to be the opposite over the hypotenuse, and side B is the hypotenuse. Okay. So in this case, we know that the height of the triangle is 9.3. So just to kind of illustrate what could happen, what if I told you, let's change the values a little bit. What if I told you that angle A was 51 degrees, side B was 12, and side A, opposite angle A, is 7. Okay, well, right away you should be able to tell that A, that 7, is shorter than the height, 9.3. Okay, and you can kind of tell on the graph, it's pretty short, right? Let me go back to 7 there. If I were to move side A around, what should we observe happening? Or what, more specifically, what does not happen? Okay, as we move side A back and forth here, again, it's only a length of 7, it's too short. It will never be able to reach down and connect with the bottom side and form a triangle. So if I told you angle A was 51 degrees, side B was 12, and side A was 7, and that we have a triangle, I'm either lying to you or I'm mistaken. Maybe I have the wrong value somewhere. Okay, so just with those 3 pieces of information, with the angle of 51 degrees, the side B is 12, side A is 7, there's no triangle. Okay, there's a mistake somewhere. We don't have the right values. Okay, so that's what can happen to give us no solution. Okay, the values just don't work to make a triangle. Okay, so what happens if the side A, the one that we're given, was actually equal to the height? Okay, so as I swing this around, it just touches once right there. So if the height, or sorry, if the opposite side of our given angle has a length that's equal to the height, then I know I'm going to get a right triangle, and I only have that one triangle to work with. That can happen in terms of a law sine and cosine situation. It's not really interesting because it's just a right triangle, and so you don't have to use law sines. You could just solve it using right triangle trig. Okay, so we're not too worried about that situation. So let's go back to what happens if that value is a little longer. Okay, so now angle A is 51, angle B is 12, or sorry, side B is 12, side A is 10. Okay, so now side A is longer than the height. Okay, and as we swing this back and forth, you'll notice that this side actually connects, side A actually connects with the bottom edge twice. Okay, and that's going to create 2 triangles. One triangle occurs if we swing outwards away from our angle, and we get a triangle. And the other happens if we swing inwards towards the angle, we get a second triangle. Okay, and this is where we get 2 possible solutions for the given information. Okay, so if I have a triangle, angle A is 51, side B is 12, and side A is 10, there are technically 2 triangles that exist that satisfy that given information. Okay, and when we're solving problems like this, we need to find both of them. Okay, now one nice thing to note here is if we swing that side A outwards away from angle A, the angle that it forms in the bottom, the angle, we could think of this as angle B here, that it forms with the bottom side of the triangle, it's going to be an acute angle. And if we swing it inwards towards angle A, this angle B is now an obtuse angle. So we're going to get 2 triangles. One triangle where we have this acute angle B, and another one where we have the obtuse angle B. Okay, and so that for that to happen, we need, again, the length of the side opposite angle A to be longer than the height. But we also need side A, the opposite side, to be shorter than the adjacent side, so the side B in this case. So 10 is less than 12. What happens if the 10 gets longer? What if side A becomes like 14? Okay, if side A is 14, again, we can swing side A left and right, inwards and outwards. Oops. What happens if we swing side A outwards? We get a triangle, right? And we have an acute angle. What happens if we swing B back to the left towards A? Well, notice that because the side A, which is opposite angle A, because it is actually longer than B, the end point of side A actually swings past angle A. It doesn't actually connect to the bottom side of the triangle. So if the opposite side is longer than the adjacent side, so if side A is longer than side B, we again only get the one triangle if we swing outwards. Okay, so again, if it's too short, no solution. If it's too long, one solution. And kind of Goldilocks here, if it's in the middle, if it's just right, we'll get 1, 2 solutions. Okay. And with the graph here, let's look at what happens if the angle we had was obtuse. Unfortunately, the illustration that he created here is a wonderful graph illustration. He capped the angle at 90 degrees. So just imagine that we have an obtuse angle here. Okay, so if side A is shorter than side B, so if side A is just a little bit shorter, okay, as we swing it around, again, notice there's no triangle, right? I can't get it to touch the bottom side. So in order to get a triangle, it actually even won't work if it's equal to the length. If side A and side B are equal to each other, it doesn't really create a triangle. It just touches at the bottom corner. Okay, so in order to get a triangle here, we need the opposite side to be longer than the adjacent side. So we need, like in this case, we need this to be 15, because then it will touch as we swing to the right. And if we swing it to the left past our obtuse angle, again, imagine that this is an obtuse angle here, it will go past the angle. So if we have an obtuse angle, or even a 90-degree angle, like is illustrated here, in order to get a triangle, the side opposite your given angle has to be longer than the side adjacent to the given angle. Okay. All right. Let me just let's look at a summary of this real quick. So there are just several situations here. Again, there's kind of 4 main cases if we have an acute angle. Okay. So here first we have A is acute, and there's 4 situations to worry about. So if A is shorter than the height, and again, I'm using letters A and B here, and angle A. Don't get attached to these letters. It does not have to be angle A. That's the angle given to you. It could be angle B or angle C or some angle that we don't use a letter for. Okay, so don't always think in terms of A's and B's and C's and stuff. Okay, I'm just using the letters right now as a reference point. Okay, so in this case, again, side A is shorter than the height of the triangle, then that means there is no solution. Okay, there's no solution if the opposite side is shorter than the height. The next situation is if the opposite side is equal to the height. So again, what if A is equal to H? We then have 1 solution. It's just a right triangle. It's not even the law of sines. It's just a right triangle. All right. The next one is what happens if A is bigger than the height. So I'm going to write it the reverse. I'm going to write H is less than A. So the height is the height is less than side A, or side A is greater than H. But side A is also less than side B. Okay, and this is where we get 2 solutions. And that's because the opposite side is longer than the height, which means it will connect to the bottom side and give us a triangle. But it's shorter than the adjacent side, which means we can swing it outwards or swing it inwards. We saw that on the illustration. So we end up getting we swing it outwards to get the acute angle. We swing it inwards to get the obtuse angle. Okay. And then the last situation, this is if the opposite side A is greater than the adjacent side B, and this time again we get 1 solution. Okay, so these are kind of the 4 cases for having an acute angle. All right, if that's what we're given is the acute angle. And again, don't get attached to the letters. Also, do not get attached to the positioning of these triangles. Okay, it does not always have to be angle A in the bottom left corner. Right, it could be angle C at the top that we're given. right? And so the pictures that I'm drawing here, you could think of rotating them or flipping them or changing the letters. Doesn't matter. Positioning, the orientation of the triangles doesn't matter. The idea is still the same. You have a given angle, the opposite side, and the adjacent side. And the height is measured from the angle between the two sides. Okay. All right. The other situations we need to look at is if A is obtuse. Okay, so if A is greater than 90 degrees. Here we only have two situations that we have to deal with. If the opposite side, A, again, because it's opposite our given angle A, if A is less than or equal to B, so if it's not long enough, there is no triangle. Okay, and then the other option is if we have an obtuse angle A, if the opposite side, so if side A is greater than side B, so if it's long enough to actually touch, if not longer, then we have one triangle. So these are the situations that we have, the categories, the breakdown of the side angle triangles. And so we can hopefully know, do we have a triangle that exists? If not, we're done. Right? That's it. If it's acute, that's possible. It's possible, and obtuse, it's possible to have a triangle that doesn't fit the information we're given. Okay. If it's obtuse, you could have possibly one, at most one triangle that works. If it's acute, the angle that we're given is acute, then we could have one triangle. We could also have two triangles. And if we have two, we need to find or work with both of them. Okay. All right, so we'll look at some examples in some of the next videos here.